Hello everyone, today I'm presenting our work, Dual Hierarchical Integration Network of Multigraphs for Connectional Brain Template Learning. This work has been done at Basira Lab by myself along with Abdurrahman Beyaz and was supervised by Dr. Islam Rekik. Brain multigraph is a way to jointly display the different connectivity types, functional or morphological, between anatomical brain region of interests, ROIs. Brain multigraph datasets are used to investigate connectomic patterns in both healthy and atypical populations. A connectional brain template, CBT, can be described as a form of average of a brain network population. A well-centered and representative CBT is a powerful tool in brain graph classification as well as evolution prediction. Typically, each graph is represented as a symmetrical weighted adjacency matrix. A multigraph subject having graphs stacked together is represented as a tensor. Brain networks have the characteristic to display modularity and hierarchical structure. From the connectivity of ROIs, clusters of nodes exist, creating modularity. Higher-level clusters on top of these clusters can be formed, thus a hierarchical structure. For a population of brain networks, how can we realize such important traits and their effects? Previous methods for creating a graph representation for a multigraph population are netnorm and DGN. For the representative CBT estimation task, DGN is the state-of-the-art method. NetNorm uses a nonlinear fusion method to integrate the most representative edge features. Despite having promising results, it is prone to accumulate errors because of independent methods. Its vectorization method is agnostic to brain network topology. DGN is the first method to use graph neural networks for such a task. It integrates upon the edge features of ROIs and learns node embeddings locally in an end-to-end fashion. The shortcoming of DGN is that it only does integration at the node level, thus does not use any further information the graph might carry. To overcome such limitations, we propose Dual Hierarchical Integration Network, Dual-HINet in short. Dual-HINet is a novel graph neural network architecture for integrating a brain multigraph population into a CBT that considers the duality of node-level and hierarchical cluster-level connectivities of the brain network. It achieves this by dual blocks that utilize edge-conditioned graph convolution, where the second block uses a GCN that learns multigraph clustering in an end-to-end fashion. By doing so, it is the first CBT method to capture brain connectivity modularity and hierarchy at the group level. With a novel loss objective, clustering assignment and CBT centeredness is jointly learned. Now, let's see the GNN architecture itself. The initial subject multigraph is fed to both blocks. The first block outputs local information of ROIs from the multigraph subject, using a GCN that generates node embeddings. The second block gives information of how nodes are connected as clusters. In order to do so, a GCN that learns cluster assignment is used. The previous layer's nodes are mapped to clusters, and the edge features are transformed to represent cluster-to-cluster connectivity. The new coarsened multigraph enters a GCN which gives cluster node embeddings of the current layer. With deeper GNN layers of the second block, a hierarchical structure can be learned. After we obtain various layers of embeddings, we max pool them to identify the most discriminative attributes. We then concatenate them and pass them through a fusion layer and have a single graph representation vector for each ROI independently. We replicate this vector, then compute absolute pairwise differences and obtain a subject bias CBT. To evaluate the output CBT, we use a joint objective loss function. For population centeredness, we take k number of random subjects and compute their mean Frobenius distance with the CBT. For generalizability, we measure the dissimilarity of the assignment on L layers between k subjects. We train our model on 4 large-scale connectomic datasets from the ABIDE public dataset, which includes left and right hemispheres of 155 normal control and 155 subjects with autism disorder. Each subject is represented by 6 cortical morphological brain networks upon 35 ROIs. We use threefold cross-validation technique while training. To evaluate centeredness and topological soundness, the Frobenius distance and mean absolute error in node strength of the estimated median CBT against the population of multigraphs was computed. There were 4 variants of our model, 2 ablated versions, where the node-level based block was removed, each model having 1 and 2 number of clustering layers. All models were trained for 150 epochs. Every variant of our model statistically significantly outperformed the state-of-the-art DGN on all 4 datasets. So, in summary, Dual-HINet is the first GNN method that considers the brain network modularity and hierarchical structure for estimating a CBT for a population of brain multigraphs. Our model significantly outperforms state-of-the-art in the CBT representativeness task. In our future work, we would like to generalize our model for directed brain connectivity networks and focus on the integration of multi-resolution graphs. We will also investigate the relationships of training multigraph subjects and their effect on CBT estimation. Thank you for your attention. Feel free to check out our recent review paper on GNNs in network neuroscience covering recent GNN architectures for brain connectivity integration, classification, super-resolution, and more. You can also visit the GitHub repo of the paper. For more, please visit us at basira/lab.com. Be sure to like and subscribe and leave a comment.